Okay, everybody. Hey, so by now you realize there is a substitute for today, Friday's class. Um, but this video is to go over the gas-free response practice number one, and there's also a video that's going over gas-free response practice number two. And so the answer keys are posted, but you can also watch this video to see the answer key. So sorry, I'm not there today. I usually don't like to take days off, especially I don't like to miss the AP classes because we have so few classes before May 2nd. But something came up and I had to take advantage of it. So watch the videos, or I guess first work by yourself or work with some people around you, and try to answer the questions to the gas-free response, and then check your answers with this video or with the answer key, and you know make sure you understand it. If you still don't get it after watching the video or looking at the answer key, then you're probably going to want to stay after sometime next week and ask some questions. Okay. So again, this is gas-free response number one, and then the other video that's posted is gas-free response number two. And you might want to also take advantage of the time that you have with the sub. There's a couple of videos in the "In Case You Missed It" folder for this past week. There's just review of kinetic molecular theory and gas law. So you might want to check those videos out as well. You don't have to, but once you complete the gas-free response stuff and you understand the answer to those questions, then go ahead and complete your 3-2 assessment, complete your concept check, and we'll be beginning the second part of Unit 3, which is all about enthalpy and heat. We'll start that next Tuesday. All right, so let's jump into free response one. All right. So here it says observations about real gases can be explained at the molecular level according to KMT, kinetic molecular theory of gases, and ideas about intermolecular forces. Explain how each of the following observations can be interpreted according to KMT and IMFs, including how the observation supports the correctness of the theories. Okay, so let's get into it. When a gas-filled balloon is cooled, it shrinks in volume. This occurs no matter what the gas is originally placed in the balloon. All right, well, let's go to it. All right. Okay, so as temperature decreases, we know the average kinetic energy of the particles decrease. This means the particles move slower on average. Okay. This decrease in energy and amount of collisions, this decreases, the energy and the amount of collisions the particles have with the side of the balloon, which means pressure decreases. The balloon decreases in size until the pressure equalized with the atmosphere. So the atmosphere's pressure doesn't change, but if the particles inside the balloon slow down, the balloon is going to start to collapse due to the pressure of the atmosphere until it's equalized again. So this is kind of a Charles' law question. As temperature goes down, volume has to go down in order to maintain a constant pressure, and that constant pressure inside the balloon is equal to the pressure outside of the atmosphere. Okay? All right, let's keep on rolling. All right, when the balloon described in part A is cooled further, the volume does not become zero. Rather, the gas becomes liquid or solid. So now this is when intermolecular forces are turning on, and the substance is either condensing and freezing, or just deposing, right? Oops. So let's go back. All right. So as the particles slow down even further, intermolecular forces start to cause the particles to attract to each other. This causes them to condense and then possibly freeze, or cause them to depose, right? So that's the other way you can go from a gas to a solid. You could condense and freeze, or you could depose, which is the opposite of sublime. All right. So that's a pretty straightforward one. All right, let's go back to the next one. When NH3 gas is introduced to one end of a long tube, while HCl gas is introduced simultaneously at the other end, a ring of white aluminum chloride is observed from in the tube after a few minutes. The ring is closer to the HCl end of the tube than the NH3 end of the tube. And this is mainly because HCl is heavier, so assuming they're at the same temperature, both particles have the same average kinetic energy, but because HCl has a greater molecular mass, right, 35 plus 1 versus 17, so this has a higher molar mass, so it's going to be moving slower on average. So as it travels down the tube, it's not going to make it as far down the tube as the NH3 because NH3 is faster, so it's going to be closer to the HCl than the NH3. So let's make sure we have that explanation locked down here. Okay. So assuming both gases are at the same temperature, this means they have the same average kinetic energy. HCl has a greater molecular mass, so on average, its particles move down the tube slower than the ammonia. The particles meet closer to the HCl side of the tube because they move slower, because they have more massive particles. All right. Sounds good. All right. Why does a flag wave in the wind? That's weird. It's a weird question to be on an AP exam, but yet it was. All right, let's see. All right. You can say the wind accelerates gas particles, or you can say wind is accelerated gas particles, right? That's what the wind is. The particles collide with the flag with much greater forces because they have greater kinetic energy. This causes the flag to move, AKA wave. All right. All right, so that's the first page. Hopefully those all make sense to you, and using KMT and intermolecular forces to explain some of those phenomena. All right? All right. So let's get to the balloon question. Let's get to the balloon question here. All right. So we got three. Can I count? All right, we got 5 balloons, and it looks like they have equal volumes, okay? CO2, one's full of CO2 gas, one's full of oxygen gas, one's full of helium gas, one's full of nitrogen gas, one's full of CH4 gas. So assuming they're at equal volumes and they're at equal pressure and at equal temperature, that must mean you have the same number of particles in each one. And we could probably calculate those number of particles if we knew the volume, because we were given the pressure here and the temperature. If we knew the actual volume of those balloons, we could figure out how many moles of each gas we have. And we have this equal moles of each gas. So we have the same number of particles here, the same number of particles here. So we've made those conclusions, okay? Now, other conclusions. They're at the same temperature. What does that mean? Same average kinetic energy. So again, before we read any questions, same average kinetic energy, I know this is the slowest. How do I know it? Because it's the heaviest. CO2 has a mass of 44. I know this would be the second slowest because oxygen is 32. This would be the next slowest because nitrogen's 28. This would be the next slowest, methane, 16, and helium has a mass of 4, so helium particles would be the fastest, okay? Just kind of all have equal number of particles, but helium would be moving fastest on average because it has the lowest particle mass, and CO2 would be moving slowest on average because it has the highest particle mass, or the greatest. Something else to kind of think about, since I have equal particles, I know the mass inside here is greatest and the mass inside here is least because same number of particles, but each of these particles only weighs 4 AMUs, each of these particles weighs 44. So the total mass in here is the greatest and the total mass in this balloon over here is the least, all right? So just kind of thinking about it. So another thing we could rank is densities. So this would be the least dense because it has the least mass in the same amount of volume, and this would be the most dense because it has the most mass in the same. Now, I don't know if density is a question here, but those are all things we should be thinking about and conclusions we should be jumping to based on we have same volume, same number of particles, same temperature, same pressure, okay? So, okay, part A, what has the greatest mass? Well, CO2. Why? Same number of particles, but each particle weighs the most there, okay? So let's see what we have on our answer key. All right. The balloon with the greatest mass would be the carbon dioxide balloon. All balloons are at the same temperature, the same pressure, the same volume. This means the number of particles is equal in each balloon. Each moles of gas are equal. Because CO2 particles have a greater mass, greater particle mass than the other gas particles, it would have the greatest mass overall. All right. Make sense? All right. Compare the average kinetic energies of the gas molecules in the balloons. Explain. This one's an easy one. Don't make it complicated. They are equal. The average kinetic energy of the gas molecules in each balloon are the same. They're equal to each other. Why? Because they're all at the same temperature. That's it. Same temperature means same average kinetic energy. All right. Don't fall for the trap. The CO2 is slower, but because it's more massive, same kinetic energy. Right? Which balloon contains the gas that would be expected to deviate most from ideal gas behavior? So, because we're not at an extreme pressure, right, we don't have to worry about particle volume, and because we're not at an extremely low temperature, we don't have to worry about intermolecular forces. But the gas that would deviate the most from ideal behavior, because we're not told extreme conditions, it would be the gas with the greatest intermolecular forces. So this question is asking which of these gases has stronger IMFs. So if we take a note, all of these are nonpolar. Okay, so obviously helium's nonpolar because it's just an atom. Obviously the diatomic ones are nonpolar because they're bonded to themselves, so there's zero electronegativity difference, so nonpolar bonds equal nonpolar molecules. Now CO2 has polar bonds, but remember CO2 is symmetrical, it's linear shape, so it's a nonpolar molecule. And CH4, remember the carbon-hydrogen bond we say is nonpolar, but even if it was a polar bond, tetrahedral shape with all the same ligands means a nonpolar molecule. So all these are nonpolar, so the only IMF they have is London dispersion. Which one has the greatest London dispersion? CO2. Why? Because it has the most electrons. So CO2 would deviate from ideal behavior the most. Okay, so C should be CO2, but let's make sure we got it right on the key. Okay, the CO2, so the answer would be the CO2 balloon would deviate from ideal behavior, the explanation. The stronger a compound's intermolecular forces, the more it will deviate from ideal behavior because the ideal gas law ignores intermolecular forces. All the gases here are nonpolar, so the gas with the most electrons will have the strongest London dispersion force. CO2 has the most electrons of all the gases, so it has the strongest London dispersion. Yes. All right. All right. 12 hours after being filled, all the balloons have decreased in size. So what does that mean? It means the gases are effusing out of the balloon, escaping through a tiny hole out of the balloon. Predict which balloon will be the smallest after 12 hours. So it's asking which gas will effuse the fastest, leaving the balloon with the least amount of gas particles inside. Okay, so which one of these gases will effuse the fastest? Answer, helium. Why? Because it's the smallest particle? No, because it's the lightest particle. So if you say smaller, you are wrong. You have to say lighter, okay? Lower mass. So helium's moving the fastest, so its particles are going to have a greater opportunity to escape through that hole. So after 12 hours, more of this gas has escaped, so you have less gas particles in here compared to the other balloons, so it's going to end up having the lowest pressure, and it's going to be the smallest in size because of it, because the atmosphere will be able to crush it down, crush all of its dreams. Okay, so helium. And why? Because it's effusing the fastest. Why? Because it's the lightest. Let's see if the answer key agrees. Okay, the helium balloon will be the smallest. The smallest balloon would contain the gas that has the fastest rate of effusion because it loses the most particles. It should say it loses the most particles. Yes, my wife is an English teacher. They all have the same average kinetic energy. Therefore, helium has the fastest average velocity because it is the least massive. Helium particles are moving the fastest, therefore they will have more opportunities to escape through the tiny hole, which means they will escape faster. They will effuse faster. So the helium balloon will be the smallest. All right? Okay, so that takes care of gas practice number 1. There's also a video for gas-free response practice number 2. That has more questions, so it's a longer video. But make sure you understand how to answer all those questions, and work on your 3-2 assessment and your Unit 3 concept check number 1. And don't forget to do the bonus of the day. And I'll see you next week. All right. Sorry I couldn't be there today, but understand I am having a good time where I'm at, and you're probably not having the best time right now, or maybe you are. I don't know, but kinetic molecular theory doesn't get any more fun than that, right? All right. Have a good one. Be nice to the substitute. Thanks.